Okay, so this is the last set of slides. It just seems like this chapter goes on forever, so I apologize. In most books, it is actually 2 chapters, which is why it's supposed to take about 3 weeks to cover. And one of the things I mean, maybe I shouldn't complain about the book, but I don't like about the way the book is set out is they give you these problems with minimal background. So I'm actually trying to give you a little bit more background on how to do these problems. Um, it's true that they're all kind of done the same way, but each one sort of has its own, I don't know, verbiage and style for finishing or doing problems. Okay, so first thing we're going to talk about is selective precipitation. And again, I'm going to take a number line approach to this. And what we want is we want to be able to precipitate 2 ions so that really you're just precipitating one. So you're going to have a precipitating agent, and that's going to be the anion. And then you have 2 metal ions in solution whose concentrations you want to make so that they're very different from each other. That's the separation idea. So let's say you have 2 ions at 0.1 molar and you want to separate them from each other. Basically, you precipitate one out and you leave the other one behind. And that's going to be based on molar solubility and the equilibrium constant that you have with that particular precipitating agent or anion in solution. So let me sort of go over what it means to be effectively separated, right? It just means you have a concentration of 100 times or more, okay? So there's one ion will be 100 times less than the other, or one ion will be 100 times more than the other. But since we're precipitating, I suppose it makes more sense to think, right? Like I'm going to drop one concentration to be 100 times less than the other. Then you have one metal ion as in precipitate form, and you have one metal ion in solution form. Those can be further separated by filtration or separating in some other means. The degree of separation is just the ratio of the ion concentrations. So you're looking for 100-fold. So you take the ion concentrations, the one that stayed constant and the one that precipitated, and you divide them and you try to get 100 out of that. Okay, that's effective separation. So let's do sort of a number line approach to sort of see what we're doing. And we'll do that when we look at this problem. We'll say I have 0.1 molar manganese, I have 0.1 molar nickel, right? They're both in solution. Can they effectively be separated by hydroxide ion? So let me sort of draw out for you what we're doing and use, again, like a number line approach. Okay, so here's the data from the slide. It was 0.1 molar manganese, 0.1 molar nickel. I'm looking for the solubilities of manganese hydroxide and nickel hydroxide. Now these have the same form. So when you look at these, the manganese hydroxide is more soluble. So this is more soluble here. And in my number line, what I'm going to do is this. This is the concentration of OH minus. Okay. I have like a 0, and then I have a infinity, but you can't really do that. But this is the large size. But I'm going to still put infinity, and hopefully you'll take that with a grain of salt. Aha, salt, get it. Anyways, yeah. So which one precipitates out first? Well, it's the least soluble that will precipitate out first as you increase the hydroxide ion concentration. So in other words, if I make my line better, start here, right, and I start increasing the concentration of the hydroxide, what will happen is the concentration of nickel will begin to drop. Now this is sort of taking a play on the solubility curve idea. It's not really a straight line unless you use logs, but this concentration begins to drop. And this will be the concentration of nickel, okay, that is going down, because remember, the manganese is more soluble. So I'm starting at low hydroxide, increasing to high hydroxide. Nickel starts precipitating. It has the lower solubility product. Then what happens is the manganese begins to precipitate out. And that'll go down. That's supposed to be a slope that's the same. Sorry. right, at the same rate that the nickel ion concentration will be going down, and now this will be Mn2+. Now think about what's happening at this point. I have, at this point here, once I get past that point, all of this means that both the manganese and nickel are precipitating out at the same rate. In other words, I can't get a more effective separation by going to a concentration higher than this value. On the other hand, below this value, neither precipitates because neither one of them would be insoluble at that hydroxide ion concentration. So those points are what determine two things. One, when the effective separation is its highest, and it also determines the range at which there's only one ion concentration that's changing. Okay. Again, there's basically three regions, right? There's no precipitate here. This is one ion only. And this is both. And the both ions precipitating is not what's useful to us here because we don't care about getting them both out of solution. We want to separate two metals from each other. So what we need to do is this. We need to figure out what concentration that precipitates out the more soluble compound. And then we also then want to know at that point, just hypothetically, right? We want to know where those two intercept. We want to know the concentration of nickel at that concentration. And then the effectiveness of the separation will be calculated based on the original manganese concentration because manganese hasn't started precipitating at this point here. It's only started precipitating past that point. But the nickel has been dropping this whole time while one ion precipitates out. Okay, so we need to calculate the concentration that the nickel reaches as we begin to hit the saturation or the solubility curve for the manganese hydroxide. So we're going to go ahead and do this calculation first. First calculation has to be this. When does manganese start precipitating out? Now I'm going to assume the hydroxide is the equilibrium concentration. So I'm going to go like this. I'm going to say concentration, or let me write the KSP expression. KSP is concentration at Mn 2 plus times OH minus squared. I'm interested in the OH concentration where the precipitation starts. And so I'm going to write OH, I like to rearrange and put this on one side, is equal to KSP over the concentration of Mn 2 plus. And then I need to take the square root of both sides to get rid of that. That'll be my hydroxide ion concentration where the more soluble ion begins to precipitate out. So this is my first calculation that I do there. That's one. So I'll go ahead and do that. Oops. And that'll be the square root of, and then KSP for the manganese, 1.6 times 10 to the minus 13. And then the concentration is just the given concentration is 0.1 molar. Oops, 0.0.10 molar, like this. That ends up 1.26 times 10 to the minus 6. So that's the hydroxide ion concentration that starts precipitating out the manganese. And then the next calculation I do is this one. And to do that, I use the hydroxide ion concentration I just calculated. So now what I'll do is I'll say KSP, right, this is calculation number 2, is equal to the concentration of nickel times OH minus squared. And then I'm going to write the concentration of nickel is equal to KSP divided by the concentration of hydroxide 2 plus. And I'm going to make this distinction so it's clear where this is coming from. This is the one that's causing the manganese to precipitate. It's that value there. And that's going to be 5.48 times 10 to the minus 16 divided by, and then the hydroxide ion concentration is this 1.26 times 10 to the minus 6 molar squared. Okay, so now the concentration of nickel comes out to be 3.425 times 10 to the minus 1, 2, 3, 4. Like that, molar. Okay, so that's the concentration of nickel when the manganese would start precipitating out if you went to a higher concentration, okay? Or when manganese is at the solubility limit for its concentration. So then, if you want to calculate like the effectiveness of the separation, right? Then what you do is you take like this. The degree of separation is simply going to be the 0.10 molar manganese, because its concentration didn't change, divided by the 3.425 times 10 to the minus 4th molar for the nickel, because that's the one that's been changing. And that ends up being 290 according to my ancient calculation. Let me double check real quick. Yeah, so that worked out 290. Now, there's a couple other ways this question gets asked, right? It says, what is the pH range for the separation? So that could actually be the question itself. What we just did was calculated how effective this separation is. But if you wanted to know, like, what's the pH range in which precipitation occurs for one ion, then you need to calculate a third point. And the third point's this one here. This is the concentration of hydroxide that'll start precipitating out the nickel. And then you have to convert that into pH. So we'll do that on the next slide. Okay, so now what we're going to do is we're going to do the calculation for point 3. I just sort of recopied this and then I just wrote this down here, that this is what the OH concentration is here. Now we need to know what it is at point 3. So that actually is the concentration of nickel ion that starts its precipitation. So just like we did this calculation for manganese, we're going to do it now for nickel. So KSP is equal to the concentration of nickel, 2 plus, times the concentration of OH minus, like this, squared. And then we're going to solve it for the concentration of OH minus. So by analogy, that would be this. And then that's for nickel, 5.48 times 10 to the minus 16 divided by 0.1. That whole quantity, the square root of that. So that's 7.48 times 10 to the minus, let's see, what was it? Minus 8. Okay, so now what I'm going to do is calculate pOH for both of those values and the pH for both values, and then we'll have our pH range in which the separation takes place. Okay, so I did the calculation, and what you find is the pOH is 7.13 and 5.90, and then the pH is 6.87 to 8.10. Now, here's what you have to remember, too, in terms of directions in which you're going, right? If I was building another number line like this, and I was doing it on pH, right? This is hydroxide going up. So if I put high pH over here and low pH over here, so let's say 0 and 14, right? Then between 6.87 and 8.0, so if this is 7, right, then between 6.87 and then 8.0, that's the way the solubilities will be changing. That is, as I'm going from low pH to high pH. Below 6.87, nothing is happening. And between 6.87 and 8.10, one ion precipitates, mainly nickel, and then beyond 8.10, everything's precipitating out of solution.